You're comfortable taking notes? Okay.
Okay, at least we'll
All right, so we are going to start a topic that takes us a little into more advanced area of linear algebra. And we start appreciating more columns of matrices from now on. Now, we've seen that before. You know why columns of a matrix are important. We use it in LU factorization. That was using a second way of multiplying matrices. That was a very convenient way of factorizing a matrix. We're going to learn about vector spaces. This is the topic of the next 2 and 3 lectures probably. But we want to learn how to work with a collection of vectors and derive conclusions about solutions of linear systems, whether those vectors are independent or maybe one of them is a combination of other ones, and what does it mean to be a linear combination of other vectors, and all these topics. We're going to learn some new terminology, and we're going to see Rn, high dimensional spaces. Now, 2D and 3D and 1D, we're going to cover it today. These are things that you've seen, and it's very intuitive for you to grasp because 3D space is the world we live in, spatially speaking. But we need, if we want to talk about high dimensional problems, then we need to understand and appreciate high dimensional spaces. That's where a lot of time data lives. And some more advanced topics on factorization that hopefully in the end of the third lecture on this topic, maybe we cover that. But definitely in the lab sections, you will see coding examples that you can calculate that. So first thing I'd like to cover is the Euclidean space. Now this is the traditional space that we all know. Ancient Greek geometers introduced this space, and that was the space where we could understand the physical world and universe around us. So it was very easy to imagine an object, and it is now, this object is penned in the 3D space. Now, assuming the space is flat, as we see, we can think about any point, let's call it x, y, and z, with respect to an origin, we call it O. We can decompose this to different components, 3 components as x, y, and z. What it means is that you can move along x direction independently, and then move along y direction independently, and then move along z direction independently. And you can be at this point x, y, z. And you could first move along y and then x and then z, right? Or z and then y and then x. Everybody's comfortable with ancient Euclidean spaces? We are not going to make the space curved. That's what you will learn in a theoretical physics course. Luckily, we stick to flat universes. Until the last lecture, maybe, we're going to talk about a classifier as separating 2 circles. It's a very surprising result. Real line. This is the building block of what we're going to talk about. Everything we talk about is made of this set. So the set of real lines is something that intuitively you are all familiar with. All the numbers you know, all the numbers, negative, fractions, rational, positive integers, right? All of them in one set. And we use this standard notation, the blackboard letter. It's hard to write it, but you can write it like this. And this is the set of real numbers. And this line, this is a one-dimensional space. We might write 1D. We mean one-dimensional. Because once you have this line, you only need one value to determine where you are. And that gives you one, basically, choice. So one dimension. Now, this goes all the way, of course, to negative infinity, minus infinity, and this is plus infinity. Okay? So how many real numbers do we have in this set? Infinite number of real numbers. Can we count them? Uncountable. What does it mean, countable? Give me an example of a countable set.
Natural numbers?
Natural numbers. The set of 1, 2, 3, right? This also goes up to infinity, but we can count it. 1, 2, 3. Now, we're not going to bother you with this, but I think in a more advanced or graduate level linear algebra, this becomes very important because they might talk about infinite dimensional spaces. But we are concerned with finite dimensional spaces. Okay? Just to give you an idea that these topics you can build on it and make it more and more complicated. Some examples of real numbers. You've done this before. There should be no surprise. You assign minus 2 to a, square root of 2, a math constant pi. This is the familiar pi, 3.1415, whatever comes after that. I only know 4 digits. Euler's number, E. This is a number traditionally people were studying exponential growth in finance, in investing. It showed up there. And eventually, people settled for this letter E. There are other names for it as well, but Euler's number, I think, a lot of people call it that. And this is the base of a natural logarithm. So now if we know one-dimensional space, it's very natural to be creative and say, what if I make two of that line and then perpendicular to each other construct a 2D space? There's nothing can stop us from doing that. And all of a sudden, instead of a line, now I have a 2D plane, because independent of each other, I can move along any of the line, and then that gives me a point in that plane. I can choose this point, 0 and 0, to be my origin. And for example, I have a point here which has 2 units along x and 3 units along y. Now this notation, 2 and 3, a mathematical way to give it a name is called tuple. Tuple or tuple also, I think it's a pronunciation. This is a mathematical object. It's a name for an ordered list of objects. Not necessarily numbers. They don't have to be of the same type. It can be an image, a shape, a character, whatever it is. So an ordered list of objects is a tuple. When you say 2 tuple, means it has 2 elements. Now, ordered, that means that this is not the same as 3 and 2, right? These are not equal. But we are working with tuples that contain numbers, which we gave them in the beginning another name. It was an array of numbers, and we call them vectors if you could list them. So it is perfectly fine to write this as 2 and 3. Vectors also keep orders for us because we distinguish between 3 and 2. We don't consider these two vectors to be the same, okay? Now the set notation, R2 raised to the power of 2, this is the set of all two tuples, x and y, such that x and y are real numbers. They belong to the set of real numbers. And this notation is for set, okay? And if you remember, this was the definition notation. So R2 is the set of two tuples such that both two members of that tuple are real numbers. You do not have to call it x and y. We will see. We will use a better notation that scales up to higher dimensions. But it's very common and convenient to show them x and y for 2D space. Some examples of points in 2D space. These are just two vectors that you know already, okay? A 2 vector, another 2 vector, the origin, which is 0 and 0. You can check the size of A, which is 2. Now, there's no reason to write them as column vectors, but our convention is that by default we use columns. You could just define everything as rows, but we stick to columns. Now, if you know 2D is a possibility, then 3D, of course, is a possibility too. Let's just add another line and then give it a depth, right? If you add another line perpendicular to the 2 previous lines, you get yourself the 3-dimensional space. This is the 3D Euclidean space. It's the set of 3 tuples such that x, y, and z are real numbers. So every point in the 3D space measuring relative to the origin will have an x, y, and z coordinates, okay? So you can uniquely identify each point in this 3D space. Now, if you think about this x, y, and z, the arrows are pointing the positive direction. They are orthogonal. You may call them orthogonal coordinate system. Just because they are orthogonal, and then each component gives you a coordinate in your tuple or vector, x, y, and z. And using this frame, this system, you can identify uniquely each point in the space. Now, nothing will be different. We just add an extra point to our 2D space and vectors, and we get 3D vectors. So the origin is a 3 vector of all zeros. Okay? So the origin is always all zeros. This is a 0 vector. All right, so let's call the previous examples points. We could identify each point in the space, whether 1D, 2D, or 3D, using 3 independent coordinates. Now let's talk about vectors. What is a vector? In particular, Euclidean vector. A Euclidean vector is a geometric object. It has magnitude, length, and direction. So there is a direction. You know what is the, basically where the arrow is pointing to. That's the direction of the vector. And it has a magnitude. This is very important in physics. If you take a course in physics, they use a lot of vectors, and the magnitude and direction is very important. For example, what's the difference between speed and velocity? Right, so velocity has direction, speed doesn't. I'm assuming you wanted to say the same thing? Yeah. So you already know, if you had a basic course in physics, velocity is a vector, it has direction. The magnitude of that vector, the length of that vector is the speed. We don't talk about it yet, when next, or maybe a few lectures from now, when we talk about norms, then we're actually talking about magnitude of vectors. Now, there are other examples too, magnetic field, gravity, and so on. So a vector pointing from A to B is here. A is a point in the space. B is another point. A vector is pointing from A to B. So the origin of this term, vector, is from Latin. It means carrier. It's what is needed to carry B to A, right? You can imagine the length of that is the magnitude, and then direction, the line from B to A, that's the direction of the vector. Now this notation is used a lot in physics. We don't use it here. I think if you read the book is talking about, it's coming out of favor, is mathematical notation is usually you just write A. People used to write it like this, or maybe in the bottom, or somewhere on the side, to just mention that this is a vector. But if the context is clear that this is a vector, you don't need to make notation complicated. But in any case, that's also a valid notation. If you see it, that's perfectly fine. Euclidean vector in 2D. So if I call the origin again O, and I have a point A, so actually every point is a vector as well, right? In the Euclidean space, we can identify every point as a vector relative to the origin, right? So there is a vector that connects the origin to that point. What about the 3D space? Same idea, you just have 3 directions. Now this is something that you see a lot in your engineering courses and physics courses that you might take. There are 3 dimensions, they call it I, J, K. You have independent components. And that's how you define your vector. So your vector will be A, X along. These are called unit vectors. I, that means the length of that vector is 1. It's just a direction to point out that sometimes people write it like this as well, right? It's along the direction I with the magnitude A subscript X plus A, Y, J plus A, Z, K, okay? Do you have any question on this convention? Okay, so you already know about it, I'm guessing. So the unit vectors are I, 1, 0, 0. J is, this is a mistake, should be 0, 1, 0, 0, 0, 1. There, fixed it. So these are unit vector. You can now, we're not talking about length, but you can guess why it's a unit vector. It just moves along one direction, and one unit is the amount it moves in that direction. All right, so we can write this vector as the sum of 3 independent components, or entries as we called it in our language. They're elements, entries, components, coordinates, they mean the same thing. Or you can make it so much easier and just put it in a tuple, x, a, y, and z. What's the point of writing that all I, j, k? Once we understand it, there's really no point in writing it, unless it brings a clear benefit for certain calculations. And on top of that, we also like to write it as vectors using brackets. So that's how we write it. And of course, we write it in columns. Here, I'm just writing it in a row, but we like to put it in a column. So I know there are many notations, but they all usually mean the same thing. You just pick one and work with that. Now let's make the notation more compelling for somebody who wants to work with math, work with spaces with higher dimensions. Now, we already talked about it. If you want to call things x, y, z, I, j, k, we're going to be out of letters soon. We just don't have enough alphabet to cover 100-dimensional spaces. Even if you borrow alphabet from several languages, it's still not enough. So it's so much easier to learn counting numbers than learning multiple alphabets. So let's call it 1, 2, 3. Okay? Now, I am so glad we get to talk about this, because when I use 1, 2, 3 instead of x, y, z, it makes our graduate students super uncomfortable. So suddenly, I'm just speaking a language that nobody understands. So it's important we talk about it, why we call it 1, 2, 3, even though x, y, z might be very intuitive for 3D spaces. Now, how about following that notation, we make our unit vectors also standard. We call it, let's call it the standard unit vectors, also called basis. We will cover in future concretely what is a basis, but the name for it is basis, and you can call it unit vectors. So along I, or the first dimension, we call it E1, and the corresponding index is, corresponding entry is 1. So E2, which corresponds to J, we previously talked about, is 0, 1, 0. E3 is 0, 0, and 1. Okay? We are not doing anything significant. We're just changing the notation. Now, if I use my new notation, can I write my vector A here as each of the entries, A1, A2, A3, times its unit vector? Does this make sense? Can I write A like this? Now, if you were convinced to write ax I plus ay j plus a zk. Right? This is exactly the same thing. If it's not basically, it doesn't correspond to exactly that case for you, maybe ask a question now. We can talk about it. Okay, so can I also change the order? If I have A1 times E1, can I write E1 times A1? Would this change anything? So A is a scalar. E1 is a vector. So one is a scalar, it shouldn't matter, right? Because if we have two matrices and vectors, it matters. But with scalars, it's not important. The order should not change the result. So that means that 2 times, now we have to talk about it today, but it's the same as 1, 2 times 2. Both of them will give you 2 and 4, right? We haven't talked about it, but when you multiply a matrix or a vector by a scalar, you get to multiply all the entries by that scalar. And it doesn't matter if it's in the left or right. Okay, so I'm also free to move A1, A2, and A3 to the other side of the vector. I'm also going to substitute the vector itself here. So I have a vector, a unit vector E1 times A1 plus E2 times A2 plus A3 times A3. I'm just manipulating lots of terms without creating anything here. Okay? Now what becomes interesting here is that this is second way of multiplying matrices and vectors. The second way of multiplying matrices that we covered extensively in lieu factorization was the column, right, of the first matrix times the row of the corresponding row of the second matrix. So the first row times the first column times the first row, plus the second column times the second row, plus the third column times the third row. Now, A only has one column, so each row is just one scalar. It turns out that I can write this as the product of a matrix, which turns out to be the identity matrix, times my vector A1, A2, and A3. Now we recognize that this is identity matrix of size 3. An identity matrix times a vector, it will just leave us with the vector itself, okay? Now this looks like useless, but why it's important? Because it gives us insight into the directions that we're looking at. When we say the first row of A1, what we really mean is the direction along the first column of the identity matrix with the magnitude A1. Okay, so now we can think about it as a vector that is pointing in a particular direction, which is the column of identity matrix with a particular magnitude. This is the insight we're going to build on it to talk about vector spaces. So we realize that for a 3D space, the columns of 3 by 3 identity matrix are, in fact, our standard basis. Now we get to think about these columns as vectors, as directions. Now because it's the identity matrix, of course it doesn't have a magnitude. It's a unit vector. This perfectly matches our understanding of 3D space. And you can stack them in a row to get E1, E2, and E3. Now, is this useless or useful? You're guessing it's useful. Why it's useful? Is it useful for, yeah, go ahead.
This idea that if you have a bunch of if you have a bunch of bases put together, this can go higher than 3 dimensions, which is what we're all doing.
Exactly. So your intuition is that now with this way of thinking about it, it sounds like we can scale it up. We can start thinking about higher dimensional spaces. It was a little difficult to think about it when we were stuck with rows, that we are dealing with rows, they have different components and different directions. Now we think about columns, and this way of multiplying directions with magnitude, it looks like a natural framework for raising the dimension. So that basically is our motivation for going through this, which brings us to Rn, an arbitrary dimension. N is a natural number. R 102, or maybe for Rob 101, 101. This is a very high dimensional space, 101 dimensional vector. 101 direction to move in the space. How crazy that sounds. The model for universe, the modern way of understanding, has 4 dimensions. You have time, x, y, z. Unlike that 3D Euclidean space, time is a dimension. So R4, it is complicated enough that we can build models for universe. Of course, they're not perfect, but they're very useful. That shows that how complicated it is a 101 dimensional vector, dimensional space. So it gets a little abstract, but we need this abstraction so we can work with high dimensional spaces. These are sometimes called hyperspaces. So when you hear the word hyper, usually above 3 dimensions you can call it hyper. In 3, you have a plane. In 4-dimensional space, you call it a hyperplane. In 3-dimensional, maybe you have a sphere. You go to higher dimensions, you might call it hypersphere. So when you hear hyper, you know that you cannot probably visualize it, roughly speaking. Okay, this is just some terminology. So let's talk about Rn. Rn is just a straightforward extension of what we learned. It's the set of n tuples such that each of the entries of this tuple are real numbers. Or equivalently, using our column vector convention, you can say it's a set of all n by 1 column vectors such that each of the entries of the vector are real numbers. And that's basically the set of n-dimensional space of real numbers. You remember the movie Interstellar? pretty cool, right? In the end, they had to get creative how to visualize the space-time when they trapped into the place when the main character wanted to communicate with his daughter somehow across time. It was very difficult to visualize because it's very difficult for us to imagine how such spaces might look like. So it was very exciting to see how artists imagined that space. So when you see sci-fi movies, it's a lot of fun. You can think about these hyperspaces. Good material for sci-fi movies always. Because for creators who live in 2D space, just having a height dimension is a revolution, right? Same idea for us. If there's a dimension that we are not aware of it, could change everything. So what's the standard basis for Rn? We don't have to be too creative, right? We know that every vector must be n-dimensional. So no matter what, the vectors are n by 1 when you're talking about Rn. Now the standard basis E1, again, you get 1 in the first entry, right? First direction, zeros for all other ones. E2, the second one is 1, all other ones are zeros. En, the last one, everything is 0 except the last one. So now tell me what is E4. I'll help you with the first one. The first one is 0. The rest is on you. 0, 0, 0, 1. Great. 0, 1, you said? No, 0. 0. All the way 0. Okay. So only one of the entries can be 1, right? For a standard basis. And it's the fourth one, of course. That should not be a problem to write it down. But we need to at least understand how we form a vector using these bases. So we follow the same idea. If I have a tuple with n entries, a1, 2, and n, I'm just going to multiply each entry by its corresponding direction. I can switch the scalar and vector multiplication order. And I end up with, same as before, my standard basis times the magnitude, the entry of the vector in that direction. Now, instead of 2 or 3, I have n of them, n arbitrary natural number. Can you guess the next slide? Exactly. We're going to use the identity matrix. It's called proof by induction. You see example 1, example 2, you conclude example n. It's a very powerful proof technique. Let's stack them horizontally in a matrix, the standard basis. That will give us E1, E2, all the way to En. So again, this is an n by n identity matrix times our vector, which is nothing but just the vector itself. But it gives us the insight that each of the entry is the magnitude we are moving along each direction. So each column of the identity matrix is a vector that's a direction in the space, in this hyperspace Rn. Now, I hope this sounds obvious to you. If that's the case, that's great. This is not how most people think about matrices. We tend to think about rows more than columns. The column space is very powerful. That's how we are enabled to imagine new tools to deal with uniqueness of solution and different ideas in linear algebra. Now, of course, you know already that the transpose will switch the rows and columns, and you can guess that we can always swap rows and columns. So that's possible. But we want to think about columns from now on as directions, vectors. Okay, so the conclusion is that the columns of an n by n identity matrix are a standard basis for Rn. So when a book you read somehow talks about the standard basis Rn in one line, and you already know they are referring to these things, right? A lot of books, they might not give you explanation, but they use the terminology. So in that case, you know what they're talking about. Okay, time to grow up and talk about rectangular matrices. So far, we've been avoiding rectangular matrices. Whenever you asked, I told you, let's keep it square. Not anymore. Now, how we might think about transfer the idea into a matrix that is rectangular. Does that make sense at all? Now, we know that we have an n by m matrix. This means we have n rows and we have m columns. And we are aware that, of course, we can stack them. We can partition the matrix into columns, and we can write our columns like this. Equivalently, this is equivalent of that because we can go in both directions. We can conclude one side from the other side. So the arrow that you see is both directions. So the column J can be anything from 1 to m, 1, 2, 3, 4, 5, m, is an n by 1 vector that belongs to Rn, right? What does it mean? I have a vector, and I'm saying my vector belongs to Rn. Is there enough information for you to know what I'm talking about? It's a deafening silence. You need a yes and no. Well, maybe explain in words how you read this line, this line here.
A is a set of all real numbers in n, or like A is a set of all real numbers.
A is a set of all real numbers. Not very concise, but we know that A contains real numbers, right? And we know the dimension is n. So we know we're dealing with real numbers, and we know the dimension is n. Now, to be comfortable with this, when I say A this is in, it belongs to this set, I mean A is a member of that set. Now you immediately think about, well, how do you imagine the members of that set? We define that set to be in a particular form. So we go back to the definition of Rn. So Rn was the set of n by 1 vectors, right? Such that each entry was a real number. So if I say A is in Rn, that means A is such a vector that we have A1 all the way to An, and all of them are real numbers, okay? So this is a very compact way to say that A has that form.
Does that mean that m has to be smaller than n?
Your question was n has to be smaller than m.
No, does m have to be smaller than n?
Okay, so it's not related to this slide.
Well, I guess it's the next, or the one that we're on.
Okay, so I'll go there now and talk about it. So A takes this form, the member of set Rn, okay? So if you get stuck, just immediately refer to the definition of that set and then find out how it should look like. Now your question is that, is n greater or equal than m, or m is greater than or equal to n? Can be both. We do not impose a constraint for now.
If it's only n dimensions, then like how could you access something that's greater than like if m is greater than n, then like how can you go into like m if you're only in n dimensions?
It's a very good question. If m is greater than n, right? If the number of columns, right, is greater than the number of rows, how is that possible? Because we have, for example, 10 directions, right, in a 5-dimensional space. Is that possible?
I guess it would be directions that aren't only like in the identity matrix, like it's not just singular.
Right. So your intuition is very good that you answered yourself that, well, maybe they don't have to be orthogonal, right? We can certainly think about them as vectors, but they don't have to be orthogonal. So actually, this is the problem we're going to talk about it. Is it possible to have that? Or we are limited to a certain number of independent vectors? It is certainly the case that they don't have to be orthogonal. You don't, those bases that we define can be any complicated vectors. It's just not comfortable to write it down, at least by hand, like that, right? So that's why I call it standard, because it's the clean nominal case. So both are possible, and this is part of the topic we're exploring. What happens in different cases? Now, this vector spaces has 2 parts. Now we're in a chapter that we're covering first part. Then next chapter, 8, we're going to cover least squares, norms, and some other topics. And then chapter 9, we get back to vector spaces to cover more topics in that. So even if A is n by m, we can think about it as m columns. Each column is a vector in Rn. There is no problem whatsoever. Some examples. These are vectors in a 4-dimensional space. Why? Why should we believe these are U, V, and W are in R4? Do they satisfy how we define R4?
Well,
Exactly. You're saying that, well, I count number of rows. I have 1, 2, 3, 4, and then these are real numbers. It checks out, right? And this is a 4 by 1 vector of real numbers. So it is part of R4. Same thing for the next one, same thing for the next one, okay? So they are part of R4. That's what the question is telling us. Now the question is telling us use them to make a 4 by 3 matrix. So I'm giving you 3 vectors, and it's not difficult to see that we can put them in 2 columns of a matrix A, and that will be a 4 by 3 matrix. A rectangular matrix where we see its columns as vectors in a 4-dimensional space. Now, my advice for making sense of mathematical notation and symbols is that try to write them in text for yourself. That's what I do. You have equations, definitions, write them in text. If you can do that, then you understand them. I do that for myself. For this matrix, for example, we can write, this is a 4 by 3 matrix, right, where each column is a vector in a 4-dimensional space because they contain real numbers and so on. Then that means you can talk about it. If you can write it like that, it's not just you showing symbols to people because that's a different language. You can also talk about it and explain what you see. Another example, which is your favorite, we have more columns than rows. Two by 4. Extract columns. So we have 4 vectors, right? And they are part of R2. So the space we are talking about it is a 2D vector space. These vectors are 2D vectors. But we have 4 of them. Maybe we can visualize it. Is it a bad idea? Any objection? Here is our chance to visualize. If it's 4D, 5D, forget about it. I was even doubting myself. Maybe people figured it out. I posted a random question on Math Stack Exchange. Can you visualize 60 space to see what people react? Turns out still we can't do that. The comments were that that's an interesting question. Because it's not the same, right? It's let's say I had a 6-dimensional space and that was a machine learning problem. I wanted really to understand what's the structure of that objective function that in the end of the course we will learn about it. But I cannot imagine how it looks like because if I can see it, I know where is the optimal point. But if you cannot visualize it, then we are relying really on the mechanics and abstract calculation that we're doing. Very powerful tools, but it is sometimes hard to imagine how these high-dimensional shapes can be. All right, let's visualize it. I'm going to create, maybe I go to the previous slide. I have more space here. You can help me to visualize it. What's the starting point? I need a coordinate system. What should I call this one? Think about it. You were going to tell me X. But don't tell me X. E1. That was, I'm just trying to force you to use that. It's okay to use X5 for 2D, but let's just make it harder for ourselves. E1 and E2, let's call them our standard basis, right? And my axis, one is larger than the other one. It's okay. Okay, the first one, I have, oops, I need 8. This is not good. Now everything is positive, so I'm gonna write it like this. Okay. 1, 2, 3, 4, 5, 6, 7, 8. Do you guys have to buy papers that come with grid to plot with hand? Sometimes? Yeah, that was a thing when I was going to school. And there's a log scale for that too. And I had a course, mechanical drawing. They were forcing us to draw mechanical objects by hand. So we get good at it. There was really no point because we had CAD software. Nobody got good at it. Then they had to spend more time learning CAD software. But I got back pain and sore eyes from drawing by hand. Which makes you wonder, old drawings, they would design airplanes and ships, doing all of that by hand. And it would work. It's insane. Okay, first vector, what should I do? Call it A1, A2, A3, A4. 1, 2, 3, 4, 5, here, right? It's a vector that's connecting origin to point 1 and 5. I'm going to call it A1. 2 and 6. 1, 2, 3, 4, 5, 6. Here. That was a bad idea. I think I took this example from Jesse, now I realize how it's ordered. It's 1, 2, 3, 4, 5, 6, 7, 8. It's 3 and 7. Not a very exciting vector space. I think we can do so much better next year in this example. A2, A3, 4, and 8. Now, this is, so I have 4 vectors in one matrix. So this is the space that you can imagine. When you see a matrix, imagine its columns, each of them a vector. If it's 2D or 3D, you can actually visualize it. Okay? Now, we're not mathematically, algebraically talking about independent vectors, but let's just entertain the idea that what would it be like if one of these vectors would be, let's say, proportional to the other one. For example, I have a fifth column, A5, right? And that's 2 and 10. One, 2, 3, 4, 5, 6, 7, 8, 9, 10. It will be, right? Exactly. So A5 is like just the scaled version of A1, right? Does this add any new direction? It doesn't, right? So A1 is pointing to a particular direction. If I have another column which is just twice of that, or any fraction, right? The direction is the same. So it's not adding extra dimension, the direction for me. So you could say A5 depends on A1, right? Because we have A5 to be twice of A1. Clearly, if we know A1, we can just know A5. There is really no need to include A5 as an independent column here, because later we will see that will cause problems in solving linear system of equations. So you could say that A5 is dependent on A1. Now, of course, you could say A1 is half of A5. It's the same thing, right? Goes both ways. Now, what we want to explore is a little more complicated. It's not 2D, it's not 3D, we can't visualize, but it's not exactly a scaled version of one of the columns. What if we have A6, which is twice of A1 minus 3 times of A2 plus 5 times of A3 minus A4. Now this gets complicated because it's not that obvious to see that one column is a linear combination of other columns. It's multiplied by them and then sum them up, right? You can recover that column. This is not obvious at all. We'd like to know that because it will have consequences for us. That's the topic of linear independence, which is the next lecture. But hopefully this gives you some intuition that we're working with these directions and we want to make sure there's no redundancy in the columns of this matrix. As we will see, that will lead to zeros on the diagonal of our factorization in the modified version of LU, we call it LDLT. So when you see 2D and 3D matrices, when the columns are 2D and 3D, in fact, you can visualize, and that's a good practice. I wanted to move on, but I decided to give you another example. A is, call it B is 1, 2, 2, 4. Let's plot it. 1, 2, 3, 4. 1, 2, 3, 4. B1 and B2, right? Same direction. B2 is twice of B1. What is the determinant of B? I hope you can see. I'm writing it at the bottom. 4 minus 4, 0. That's why. We already know that when the determinant is 0, there is no unique solution to the system of linear equations. And now we think about the columns, and you're guessing already that you don't want this. You want a way to figure out if a column is dependent on other columns. Or is there a way to combine other columns to reproduce that particular column, right? Because then that means that there is a redundancy in directions you're covering. Now here is a 2D space, and you have one independent column, right? So clearly we're lacking an extra direction to cover in the space. And that's why the determinant is 0. So these are all related topics. Think about it. It's a beautiful concept, but you might want to think about it to internalize what it means. Relating the determinant and columns as vectors. Okay, so I'm going to end today's lecture with some properties of. Now those examples are just motivations, right? Next lecture we want to cover linear independence formally. Those are just motivating examples. So vector sum, what does it mean to sum two vectors? Now luckily that's not too strange. You take two vectors, you just sum respective components. x1 with x1, x2 with x2, xn with, x1 with y1, x2 with y2, and xn with yn. And you can call it x plus y. Obviously, they must be both in the same space, right? Both are in Rn. If they are from a 2D and 3D, there's a dimension mismatch. So that's the sum of two vectors. Scalar multiplication, we already talked about it. When you multiply a real number such as alpha, alpha is a part of Greek alphabet. It's a real number. So a scalar times a vector means multiplying that scalar by so multiplying every entry of the vector by that scalar, okay? Same thing for a matrix. If you have more columns, same idea. Equal vectors. We had examples in Julia about matrices. What does it mean for two vectors to be equal? Well, x and y are equal if every single corresponding elements of them are equal, right? So even if one of them is not the same, the equality does not hold. For example, if I have 1, 2, 3, is this equal 1, 2, minus 3? Is it? No. 5% of your final grade depends on this question. No, Emerald said no on chat. We'll give you a bonus in the end, Emerald. She was first. You said it late. Be fast next time. So they are not equal. hopefully you will react the same way to pizza for tomorrow. we might want to make an announcement about that in the end. Okay, said another way, if you take the difference of, we had the sum of two vectors, and then we have the definition of equality. So when two vectors are equal, that means if you take the difference of them, right, x minus y, that should give you the zero vector, the origin. And the zero vector, you can write it like this, 0 n times 1, n by 1. This is a zero vector in Rn. Now there are different notations. Some people use O for matrices, 0 for vector. But anyway, we are defining it like this. Properties of vector addition and scalar times vector multiplication. So addition is commutative. X plus y is the same as y plus x. Because we're adding every component, right? And then just adding two real numbers, it shouldn't make any difference. That's the reason. Addition is also associative. You can first add x and y, then add them to z, or you can first add y and z and then add them to x. You should get the same results. Same reason, because we are just adding real numbers in each row. Scalar multiplication is also associative. If you multiply a vector first by 2 and then by 3, it's the same thing as multiplying by 3 and then by 2, okay? Or you could just say 2 times 3, 6. I'm just going to multiply the vector by 6. Hopefully these are obvious to you. But when we move terms, we are actually mindful of these properties. The reason we can shift terms and move things around because they satisfy these properties. Scalar multiplication is also distributive. You can factor alpha and beta, another Greek letter, real numbers. You can have alpha times x plus alpha times beta times x, or you can say alpha plus beta times x. It's the same thing. Or you can have alpha times x plus alpha times y. You can factor alpha and then say alpha times x plus y. So that's all I have for today. We're going to continue on this, and we're going to cover the topic of linear independence in the next lecture, which today's lecture should motivate that. So that's it for today, and I think I'll let Professor Griesel give you some thought on tomorrow's lab and exciting things that we have.
Yeah, I thought I'd make some comments. So there's no homework due this week, so there's no formal Julia lab tomorrow. But you have a project due, which has Julia. So what we're going to do is just have a general Q&A tomorrow, and you can ask any questions about theory, programming, the project, anything you want to help you get together. You can ask them spontaneously in class through Zoom, or if you give us a heads up, Tribby and I and Lou and John can actually prepare something and have it more organized. But it's up to you guys. We will take questions live. Now, Mani mentioned the word pizza. So there's a post in Piazza that I also sent out as a mail. If 30 of the 50 students in Rob 101 will tell us what we can do better. And if your answer is nothing, it's all perfect, we love you just as you are, that's worth 2 pizzas. No, we don't care what the answer is. Be honest. And remember, anything you say is completely anonymous to all of your fellow students, okay? So we know who you are. We love all of you no matter what, but If you'll just do that, then we'll have food here tomorrow, but if, only 10 people answer, we're not going to do anything. We'll just have the Q&A. It'll be boring, but we're going to be here, and we'll be full of vim and vigor. Mani, you going to join us tomorrow?
Yeah, I will bring the pizzas.
Yeah, he likes pizza. Question.
Would you like us to reply to the post Piazza or just do the form?
Oh, okay, so there was a form earlier where I was checking on if you have any technological impediments and stuff. Filling that thing out is wonderful. For the pizza, it's answering in Piazza. And it can be just a few words, everything's fine for me. Or I could use a group study session, or I would love for you to consider doing this, and we will take your feedback in a very constructive way. Now, if you just say, you guys are the worst people I've ever met in my entire life as a human being on this planet, then we'll probably be offended. But anything short of that, it'll all be good, right,
Yeah,
Mani?
the hybrid mode is also new, so maybe you say you want more hand calculations, and we ask Trippy to solve more problems for you in recitations. Or maybe you want more coding.
More coding, yeah. Anyway,
more pizza.
That's it. More pizza, more opportunities
more
for pizza. Okay, thank you.
Thanks, everybody.